All right. To start with, I put up my name card so that I don't have to dish out my name card to everybody. That's a safe way, easy way. And if you have a handphone, you don't even have to copy this. You can just scan this, and that's everything. So a very good morning to every one of you. Thank you for coming. I understand that just now from chatting with some of you, you guys woke up at 5 o'clock. Some took trains and then bus. Some woke up at 6 and some 7, coming over, taking a few hours to reach here. I hope I won't disappoint you for your early rise and for your travel. All right, my name is Sam Zhang, Professor Zhang from Nanyang Technological University in Singapore. Just before we get into the real stuff, let me introduce myself a little bit more so that you can understand me better. I was originally born in China, Chongqing, China. And then after my master's degree, I did my university, of course, high school, university in China. And then after my master's, I went to the States in the University of Wisconsin-Madison to do ceramics. After my PhD over there, I went to Singapore. That was in 1991. So from then on, I stayed there for till now is 24 years. When I was in there first, my son was this long, 3 months. And now, when he come back, standing beside me, I have to talk to him like this. He's 1.5 something, 1.9 something, and I'm only 1.8 meter. So when I stand together with him, he's a lot taller than me. Yeah. So to cut the story short, and then. Once I get to Singapore, I never get out of the materials field. Even though that when I was in university, my major was super alloys. Super alloys is an alloy used for aerospace engine. That's also why that a few years ago, I decided to write a book on aerospace materials. So together with one of my colleagues in China, we compile that aerospace materials handbook published by CRC, a publisher in the States. And then that was in my university days. In my PhD days, I was studying ceramics, ceramic materials. After that, I went to Singapore. Then I continued on with cements, ceramic metal, doing inserts and so on. And then, because the need goes that we were going for the nano-composite thin films, nano-composite thin films and coatings. This is the field I have stayed on basically from then on till now. All these other things, like these nano-structured thin films and coatings, biological thin films and biological for coatings for medical application, all those are the later developed interests. When my PhD students want to explore that area, so I explore together with them, that created this set of books for the, biomedical field. And this is another one. There's characterization, materials characterization techniques. I invited one more from Singapore and one more from the States. And three of us compiled that book. That book, I'm very proud. Nowadays, in United States and European countries alone, some 30 universities are already adopted that book as their textbook. And this series are the nanostructured thin film coatings for mechanical properties, for functional properties, and the back of that one is this one is for coatings for clean energy. Clean energy, that's what we have in mind today to talk more about it. And this list is the one I mentioned using my book, the textbook. And the list is still going on. I wanted to show you because this list was just provided to me last week by the CRC Press. All right, so let's go to the topic we have in mind today: transparent solar cells for windows. Everybody knows, and nowadays, you know, there's because of the need to create more energy, and the coal is running out, used up, and with some years down the road, what we're going to do? Well, actually, you don't really have to worry. Solar, later on you'll see, got the tremendous power for us to tap on. The gold mine is there. The gold mine is not in the earth. It's up there in the space. All we need to do is to try to find a way to harness it. So how to harness it? That's what a materialist have to consider, have to worry. Now, this keyword is transparent. Solar cell is not a stranger to all of you. Many roads nowadays are already installed with solar cell lights. Those are the first generation solar cell. That why we worry about that? Because that solar cell, that first generation, that silicon-based ones, those solar panel, you see nowadays on some roads, they're pretty efficient, but wastage is a lot. The manufacturing process wastes a lot. Simple is that the wafer, when you make a wafer, at least it is point something mm. But actually, to harness the light, making it into electricity, you only need some like 20, 30 nanometers, that thick. The rest of them, 100 times over, is wasted. And making that waste that layer, you have to waste a lot of energy. And then that is not friendly to the earth. Then that's why we try to develop thin film solar cells. To go further on that, transparent. If you can make it transparent like this, that's in the news recently. You can see that it's June 20th, 2013, and then this guy is holding a glass with solar cell on it, transparent. And this hand is holding a glass with a solar cell. It's completely transparent. Imagine if this can be done for all the windows, then all our windows become a power source. But if you use the first generation or even the second generation solar cell, they are not transparent. They are dark. So that when it is dark, you cannot make it into window, because the window you need a light to go through. Nowadays, there's quite a number of things are going on, trying to make it work. But the problem is the efficiency. Why nowadays it's still not so popular is the efficiency. Yeah. So let me just remind you with these numbers. 10 to the power of 3, that's called kilo, right? Kilo. So 10 to the power of 3, that's a kilo. Here's 10 to the power of x. When 10 to the power of this x equals 12, we call it a tera. That you know, right? Tera. And era is 18. That many numbers of zeros behind a number. Why I'm talking about this is because here the world energy consumption in 2012 is this much. Is this much era joules. That's 10 to the power of 18, or 18 terawatts. And the annual the annual renewable fuel from ocean energy is 1 of this extra joule. Hydropower is 50 EJ, biomass, wind power, and take a look. 1,000 something to 49,000 something with the same unit, exajoule. That's 1 year for the whole world to consume 567. And if you divide that to this solar energy each year, we have a tremendous power. No problem. If we only need to harness 10%, if we only need to harness, let's see, if we only needed to harness 10% of that power, that is equivalent to more than 4,000 Fukushima Daiichi nuclear power plant. This, everybody knows that got a problem. Nuclear power plant, you build it with tremendous cost, and then it may last you 40, 50 years. After that, what? You have it buried. Buried it is still unlined in your earth, under your foot. Somewhere, somehow, or down the road, I don't know what is going to happen. So if we could harness just 10% of that energy, the world has a bright future. But the problem is how. So that needs materials list. This is the first generation solar cell, which you are very familiar with. And for this, you can immediately see that the problem. They need place. They need land. They need land place. On rooftop, yeah, some rooftop can do that. Aside from the problem, the wastage problem, during the manufacturing of this silicon wafer, installation of this on the rooftop is another challenge. So this is one of them. And transparent solar cell, yeah, that's much better. And if you make this, combine it, make it holistic design into a building, you don't need a special place. When you build a building, you just make it into this building structure. Nowadays, like when we have new buildings, like in my office building, this whole corridor up is completely glass panel, just to get more lights in, so that we can use less electricity. Imagine if we just use a coating, a thin film coating on top of that glass panel. The whole stretch of corridor is transparent with the light coming in, but also generates light, generates electricity to provide the power for lighting. That would be good. So how do we make it transparent? Let's go back to basic. The light is a wave with short and long, very long wavelengths. You know that some wavelengths you cannot see, I cannot either. And this visible light is only with this area. If the wavelengths come to that area, that range, then we can see red, purple, depending on the wavelengths. So you can separate it into 7 colors. All those, why different color? Of course, it's because of the wavelengths. The shorter the wavelengths, the higher or lower the energy? Anybody? Lower. Wrong. The shorter the wavelengths, the higher the frequency, and therefore the higher the energy. This is the high energy, and this is the low energy. So that if you, because we know this, now if we have, if we put something there, that's our glass, window glass, and if we don't put on anything, of course, everything will go through, even though we don't see it, but we can feel it. These things also go through. That's because even though you are in the room, standing by the window, and the sunshine gets on you, and you feel hot, because the high energy here, the high energy goes to your body, vibrate your skin, and then you feel hot. Now, if you put something, a coating on this, and all this color is this ultraviolet. This is infrared. If all these are blocked, only let this green portion to go through. That's the visible light. And then if we can make it completely, this guy goes through, so we don't feel the difference. The glass is the glass. We don't feel the difference. However, these two portions, we can make it into solar cell to generate electricity. That's the whole idea. How does that happen? Well, this is a band structure, meaning that if you don't understand, that doesn't matter. I give you an example. You see, when the light comes in, light got energy, right? You can feel it. If you stand under the sun, you hot. That's because you get the energy from the sun. So the sun's energy, if we use analog to demonstrate it, that H mu is a photon. Let's use a bat ball to simulate that. That ball of energy come to you. Now come to this material, any material, and then that material got electrons bonded in the system, in the atom, right? Atom consists of neutron, proton, and electrons, right? So if some electrons are free electrons, like in metal, but for semiconductor, some electrons are bound deep there. In order to make them coming out, you need to give them energy to shoot it out. So the sun, that energy, if it shoots in this material, and then that electron got that ball of energy, then it is energized. When that is energized, it will jump up. Whether it will jump out or not, depending on how energetic it is. If there's enough energy, it will jump out of this trench. There's a trench there that have to, like a high jump. Like in your physical education, you have a high jump. You need to have enough energy to jump over. Now, if you do, then this jump over, this electron is in that conduction band, meaning that now it's free to go. You know, electricity is the flow of electrons. Now, if in your conduction band, these electrons are free there, now if you put a small voltage, it's going to go. When the electrons flow, haha, you got electricity. That's how it works. This is the Einstein Equation. Don't care about the big name. It's just saying that this wavelength divide light velocity. That is your mu, your frequency. And the frequency times the Planck constant, times a constant, that constant happened to be called Planck constant, discovered by Mr. Planck, this great man. So this patch of energy is related to that wavelength. Now, as I mentioned, closer to that side, the wavelength is short. Now you have a higher energy. For going this way, you have a longer wavelength. Then you got a smaller energy gap. All right. The point is, if we can harness this energy, block that, we create a material to block that wavelength. At the meantime, if we block these wavelengths also, make that energy to convert it into electrons. Make that energy to shoot to our coating, and that will excite the electrons in the coating, so that we will have many electrons to be conducted out. That's the idea. So how do we do that? To make it transparent, the best is that to let it absorb. Nothing invisible region. But that's idealistic, too idealistic. Cannot be that way. Then, if we cannot make it absorb nothing, at least we make it absorb less. Then we can still got a transmission light, but perhaps a little bit less. That's okay. So how? One of the first thing is Dyesensitized solar cell. This working principle is like just like harnessing the plants, harnessing the light to generate oxygen. You see, you have water going into the plant, and then they also get CO2 in the air, and then with the light, then this will transform into oxygen. The plant knows how to make use of the light to create food. Oxygen is food for them. And in the end, you created carbon. This carbon is in the air to start with, and now this is in the tree trunk. So that's why that these trees you have carbon in it. Now, somebody in Malaysia student make use of this dragon fruit. That is a natural dye. Use that dye to convert that into electricity. How does he do that? Exactly what is this dye-sensitized solar cell? The pioneer of this dye-sensitized solar cell is Grizzle. He has done the pioneer work, and we have lots of applications nowadays. Even making it into flexible and to put on the cars, etc. So this is one example from the internet. You put a dye-sensitized solar cell is sitting there with lights shooting on it, and then you make this light bulb to lead. So the idea is like this. This is a dye. This is small things are dyes. Dyes has this iodine, and these particles, like here, this particle is TiO2, titanium dioxide. When this dye on TiO2, when this dye, this structure is the dye. When the light, just now I said a pocket of light coming in, like a ball, this energy shoots on it, and then this will elevate an electron, and that electron goes up to the conduction band, and this will through this TiO2 to go and then go out. That will make it make the electricity generation realized. The strategy number 2 is that we make, even though it is something is not transparent, but if you make it thin enough, it will be transparent, like a diamond. Ladies love diamonds. Diamonds, of course, you see it is not transparent at all. However, if you make it into thin film, make it into very thin enough, it will be transparent. So that's another strategy, make it transparent. And then this is the transparent. And then if you increase from this wave band, you can see that if you increase this band, all of this, with all of this, that would be great. But letting this portion go, but make use of that. That is, nowadays we have this structure, making use of this perovskite structure. This will be able to harness that top area. And if you also that make these balls, these places, use it polymer. If you use polymer, and this could make use of this area, infrared or near infrared portion of that light. Yeah, this is the observing. The first is this one, and then you also get this infrared range. This one you can see that for these people use only this infrared band. Make a coating there. This coating will absorb infrared light. That were used to generate electricity. Now the question is, hey, Professor, you already know that there is these ways. Now how come now our buildings are still not, our building windows are still not yet use these materials? Any idea? Expensive, correct. Now because the efficiency is still low. Like this one, they just make one to show you the possibility. If you want to make it into everybody's building window, that's too expensive, and the efficiency is still not good. So another strategy, you make something to reflect the light. Make this light reflect and then to do it again. Here, like you put a layer of silver there to reflect and then make the light to work for you another time. After it goes through, bounce it back. And then you're making use of the deep those infrared light with low energy, with low band gap. Those then you make it to jump 2 times, and then jump down again. Like you go up to, you put something, go up to the first floor, then go to the second floor, then you jump from second floor to the ground floor. The height, that jump is higher, so that this one would have a higher energy. So that is called up conversion. Yeah, that is showing that what is up conversion. So I'm not going to drag on to this technicalities. So anyway, that with this up conversion, you can have better efficiency. The point is to have better efficiency. Use different material so that you can have vision to go through. Making use of this ultraviolet light, and then the infrared light lower band, so that then making use of both ends and letting the visible light to go through. That's the whole idea. So the prospect, we need you to think of ways to make this work. higher efficiency, and then we can make the whole world buildings all covered with a solar cell, but you don't see it. You don't see the light getting too much dark, too dim. You see transparent glass, but in fact it has solar cell, solar power on it. So all are solar power generators. And perhaps also that in the end, this air con in the room is not needed, right? You block out this UV light, which is high heat. So you make even the air con redundant. Or you maybe for northern hemisphere people like you guys in Portland, you want to in the winter time when the sun comes, you want to let it come, but not let it go out, so that you can keep warm. All those are the good possibilities. How? Materials. As we mentioned, you know, the human civilization is depending on materials. From ancient times, from the Stone Age, as Prof. Witold mentioned, Stone Age, then Bronze Age, then Iron Age, then steels and this now microelectronics, all those are depending on development of materials. Actually, if you think about it, the whole civilization, human civilization, is depending on development of materials. It's in sync with the materials development. So we're counting on you guys and to come in to do more materials for you, for me, for the earth, for the whole humanity. If you need to do some further reading, I have something. This is my personal research. That's my personal website, and this is this website. This site is here, and actually, if you click on this, it leads you to this, and then if you click on this research by area. And then you'll see this is energy, films, and coatings. So, of course, from internet you have all many materials to read, and also the book I mentioned earlier I published a few years ago. So there's plenty of things for you to read. And with that, thank you for your attention.